Hello geometry students. In this video we are going to be approaching one of the hardest topics in all of geometry, and that is the two-column proof. What a two-column proof is a very formal way of starting with a set of things that you know and proving something more complicated from that set of things that you know in a very elegant and stepwise way that proves that every single step along the way you have a reason for what you're doing. There are 5 parts to a two-column proof that you need to be aware of. First of all, there's the given statements, the things that are assumed to be true that are given at the start of a problem. A proof statement is the thing that is proven to be correct by the end of the problem. A diagram is something that you're going to sketch to show what's going on in your diagram. This is specific, by the way, in your proof. This is specific to a geometric proof. Statements are the specific steps in between the beginning and the end, and then reasons are what justify each and every step from beginning to end. All right, so you're ready to dive into one of these, aren't you? Let's get started. So here's something that's provable. If a triangle is obtuse, what can you conclude about the measures of its two non-obtuse angles? Can you conclude that those two non-obtuse angles are definitely acute? I'm going to do that facially and then very deeply in a two-column proof. I'm going to have statements and reasons, but before we begin, let me draw a picture, a diagram of an obtuse triangle ABC. This is going to be the triangle that I refer to. Notice I put my obtuse angle at A, and I'm going to refer to this triangle throughout our proof. So my first statement is going to be the given statement. Okay, you're always going to start off with a statement of one given or multiple givens, depending on where what you're given in the problem. ABC is an obtuse triangle. Now, what can I say that's going to get me toward being able to conclude that B and C are acute angles? Well, I'm going to note that an obtuse triangle has one obtuse angle. An obtuse triangle, by definition, has one obtuse angle, angle A. And then two acute angles, B and C. Now, seeing as how the definition of an obtuse triangle says that there's two acute angles in it, I could actually technically finish right here. We're going to keep going. I'm going to prove beyond the shadow of a doubt that B and C have to be acute angles. And by the way, what's my reason? Well, the reason can either be a postulate, a theorem, or a definition of something. In this case, my reason is that it's the definition of an obtuse triangle. My next statement. Angle A measures greater than 90 degrees. Why is that? Because it's an obtuse triangle, and that is my obtuse angle. And an obtuse angle is greater than 90 degrees. Next up, all right, so I'm building this argument. I have an obtuse triangle. It has one obtuse angle. That obtuse angle is greater than 90 degrees. If I add together all 3 angles in the triangle, I get a measure of 180 degrees. That's by the triangle sum theorem. We learned the triangle angle sum theorem in a previous lesson. I can add up all 3 angles and get 180. Now, if I replace angle A with 90, the smallest possible value that angle A can take on, and actually technically 90 is even smaller than the smallest possible value because 90 is not obtuse, it's right. So I'm going to substitute in 90 degrees for angle A, keeping in mind that this number is going to be greater than 90 degrees. I'm going to use the substitution property of equality for the smallest possible value of the measure of angle A, and technically this is even smaller than the smallest possible value. Now what's the next step? I'm going to subtract 90 from both sides of this and see what happens. When I use the subtraction property of equality to subtract 90 from both sides, I get the measure of angle B plus the measure of angle C equals 90. Okay, now I'm going to write 2 statements from this. I'm going to subtract B from both sides, and then I'm going to put B back, and I'm going to subtract C from both sides. You'll see why I did that in just a second. The measure of angle B equals 90 minus C. The measure of angle C equals 90 minus B, right? I could write either of those 2 statements based on this. What does that mean? If B is 90 minus something, does that mean it's going to be smaller than 90? If C is 90 minus something, does that mean C is going to be smaller than 90? I used the subtraction property of equality to prove that both B and C are going to end up being smaller than 90 degrees. And if they're smaller than 90 degrees, what does that prove? That proves that they are acute by the definition of an acute angle because they're less than 90 degrees. That is how you do a two-column proof. Let's go ahead on to this next one. Fill in the reasons for the proof of Theorem 5.5. In Theorem 5.5, we learned that if two lines form congruent adjacent angles and they are perpendicular lines. So my givens are that angle LNM is congruent to LNP. Okay, all I know is they're congruent. I don't know necessarily that they're right angles yet. I need to prove that LN and MP are perpendicular. Now I'm going to tell you this, in these Saxon proofs, sometimes they skip steps that I would have done in my proofs. We're going to do a me proof at the very end of this. Let's just take a look at what happens in a Saxon proof. So the first reason is almost always going to be a given. LNM is congruent to LNP. I know that these two angles are congruent. That means that the measure of LNM is equal to the measure of LNP. Why does the measure have to be equal? Why, that's because of the definition of what it means for angles to be congruent. If two angles are congruent, their measures are the same. The measure of MNP is 180 degrees. Now, I don't like this one. I would have started off by saying MNP is a straight angle by the definition of a straight angle. They say that it's 180 degrees by the definition of a straight angle. And then number 4, the measurement of LNM plus the measurement of LNP, because both of these add together to make up the angle MNP, we could say that these two are going to add together to make another straight, the straight angle that we see by the angle addition postulate. Now here's another place where Saxon sort of skips a step. Notice that they say 2 times the measure of LNM equals 180 degrees. How do they get that? Well, the only way to get that is up here in this equation, they must have had another LNM. LNM plus LNM is 2 LNM, right? How would you get another LNM here? Well, you'd have to substitute in LNM for LNP because you know that they're congruent to each other. So I'm just going to state that we're substituting, okay? This is the substitution property of equality. And we can totally do that to show that these two things are congruent. It's just, in my opinion, Saxon kind of skipped a couple of steps to get to that point. And then let's see, if LNM times 2 is 180, then that means that 1 LNM is 90. That's the division property of equality. And then finally, if an angle equals 90, that means that the rays that make the angle or the lines containing those rays have to be perpendicular. And that's how we get the conclusion LN is perpendicular to MP. All right, that's the definition of perpendicular lines, by the way, that two perpendicular lines have an angle measure between them of 90 degrees. Lastly, we're going to do this last proof and then we're going to be finished. Given triangle ABC with exterior angle ACD, we need to write a 2-column proof to prove the exterior angle theorem. Remember, the exterior angle theorem is that the measure of ACD is the same as CAB plus ABC. The exterior angle equals the measure of the two remote interior angles. All right, let's get started. We're going to start with our givens, but I'm not actually going to rewrite the givens this time because it just takes up extra space that I do not have. So we're just going to say the given is that angle ACD is an exterior angle of triangle ABC. Now, how are we going to flow through this argument? Well, first of all, I'm going to note that ACB and ACD are a linear pair by the definition of a linear pair. And what that means is that when I add them together, they're going to equal 180 degrees. But I know something else that equals 180 degrees. All 3 angles in my triangle are 180 degrees. CAB, ABC, and ACB. Okay, notice I have all 3 angles in my triangle represented here. By the triangle sum theorem, those equal 180 degrees. So does my linear pair. So what can I say? If these two added together 180 and these 3 added together 180, can I just set those equal to each other? Just to be consistent here, I'm going to change this to CAB and ABC. But if I measure all of my angles in my triangle, that equals the sum of the linear pair. Okay? That's the substitution property of equality that lets us conclude that. All right, where can I go from here? Is there anything here that gets canceled out? Well, I notice I have the measure of ACB on both sides of my equation. What if I subtracted that from both sides using the subtraction property of equality? Now I have the measurement of CAB plus the measurement of ABC equals the measurement of ACD. That is almost exactly what I had to prove here. There's just one more step. I need to switch sides of the equal sign, and I'm going to use the symmetric property of equality to do that. So if A equals B, then B equals A. And I can move if I have two things on either side of the equal sign, I can flip-flop them, and that's okay. So now I have exactly the proof statement here in my final statement of my proof, and that is what I was going for. All right, that is a two-column proof. Notice we made an argument and we went step by step, rationalizing each thing with reasons from geometry as we went. And that's what I expect you to be able to do as you work numbers 1 through 30 for next time.